Okay, so today we are going to be starting our chapter on logarithms. And before we even look at a logarithm, what we're going to need to do is we're first going to really need to take a deep look at exponents. And the reason for that is because logarithms are the inverse of exponents. Logarithms and exponents are inverses of each other. And so to have even a hope of understanding how and why logarithms behave the way they do, we first need to understand exponents because our rules for logarithms come from our rules for exponents. Okay, so exponents have a bunch of rules attached to them, and they all come from this sort of initial definition that we might learn in maybe Math 9 or Math 8. What is an exponent? An exponent is simply a code for repeated multiplication. So here I have a power or an exponential term, and this power has a base and it has an exponent, and we usually just interpret this as a code for repeated multiplication. So the base is what is getting repeatedly multiplied. So we have this string of repeated multiplication, and how many times will this base appear? Well, that's governed by the exponent. So 2 to the power of 5 is really just 2 times 2 times 2 times 2 times 2. So 2 appears in a string of repeated multiplication 5 times. That's initially how we define exponents. But we start to see some patterns in how exponents seem to behave. So for example, let's say we have 2 to the power of 5, and let's say we're going to multiply that by another power. Let's say we have 2 to the power of 5 times 2 to the power of 3. If we have 2 to the power of 5 times 2 to the power of 3, well, that's just going to be 2 times 2 times 2 times 2 times 2, which is just 2 to the power of 5, times 2 times 2 times 2, which is really just 2 to the power of 3. So how many times does 2 appear in this string of repeated multiplication? It appears 8 times. And we can notice that, so again, if we were to count how many times 2 appears here, it would be 1, 2, 3, 4, 5, 6, 7, 8 times. So we have 2 to the power of 8. So here we can see that our final answer, or the exponent on our final answer, is simply the sum of the two original exponents in that product. This is true in general, and it's what we call our product rule. So here's our product rule. Product rule. And our product rule really just tells us that if we have a product of powers and they each have the same base, we take each exponent and we add them together. So that's our product rule. It is the most important rule for exponents, I would say, at least for when we are starting to learn how to generalize them. Now, that's our product rule, and we can also look at the next rule, which is our quotient rule. So let's say I have 2 to the power of 5, but instead of multiplying it by 2 to the power of 3, I divide it by 2 to the power of 3. So here, I can just expand these powers into repeated multiplication. So that's 2 to the power of 5 right there on a numerator. And this is 2 to the power of 3 in our denominator. Now we can simplify this, right? We have factors on the top that are identical to factors on the bottom. 2 divided by 2 is just 1, so we say they cancel. 2 divided by 2 is 1, so we say they cancel. 2 divided by 2 is 1, so we say that they cancel. What are we left with? Well, in the numerator, we're just left with 2 times 2, which is really just 2 squared. Now here, we can see that when we take the quotient of powers, or the quotient of exponentials, how we can simplify this in a quicker way is we can take each exponent in that quotient and subtract them to get our new exponent. This is our quotient rule. Our quotient rule is also important for generalizing exponents beyond, eventually, their original definitions of simply being a code for repeated multiplication. And we are going to start to generalize exponents in this way in the next video.